Hello. So this video is to help you with a set of algorithms surrounding the HMM for sequence labeling, in particular part-of-speech tagging. So just as a reminder, the HMM factorizes the joint probability of a word sequence and a tag sequence as a product of L pairs of factors or probabilities, one for each of the current classes conditioned on the preceding one, and another one for each of the words given its class. Now, these are also called transition probabilities. These are also called emission probabilities. And for our particular choice of parameterization, using tabular categorical distributions, we have associated a parameter with each of these probabilities. So we have a parameter lambda, a collection of parameters that we call lambda, and if we go to the row that corresponds to the previous tag of any one position, we'll be able to find the probability of generating or transitioning to the class Ci given the class Ci minus 1. Similarly, we have a collection of parameters theta, and if we go to the row corresponding to the current class for a given position I, Ci, then we can find the conditional probability of emitting from that class the ith word in the sequence. So if this level of generality makes you feel a little uncomfortable, make a short example. So suppose a sentence, a nice dog. So this is your W1. Maybe I can space these out a little. This is your W1, this is your W2, this is your W3. And by assumption, some C1 is the class for the first word, some C2 is the class for the second word, some C3 is the class for the third word, and the HMM introduces transition probabilities like that. And by assumption, we have a artificial beginning of sequence token here, just so every pair of variables has a preceding class attached to it. And we also introduce an artificial end of sequence token, just so the generative story has a stop condition. And you can see that basically you can assign parameters to each one of these, probabilities to each one of these arrows. So I can do a quick one here. So this is lambda BOS to C1. This is theta C1 to A. This is lambda C1 to C2. This is theta C2 to nice. This is lambda C2 to C3. This is theta C3 to dog. This is lambda C3 to EOS, and this is theta EOS to end of sequence. And of course I'm indexing with words, but I do mean the unique integer that you associated with each of these words or symbols. Now when you know what these tags are assigned, for example, perhaps this is a determiner, this is an adjective, and this is a noun. When you know that, then you can assign a joint probability to the non-assignments. What oftentimes will happen is that you will not know the tag sequence. You only have a word sequence, which you assume was generated according to the HMM generative story. And then you need to you're interested in either, for example, predicting what the most probable tag sequence might have been. And that's the task of post-tagging. There you would look for the tag sequence that maximizes the posterior probability for a given input. Or, for example, you might be doing you might be interested in a language model, and then what you actually want to do, you want to evaluate the marginal probability of the word sequence. That is the total probability regardless of what tag sequence might have generated this text. Right, so here you would assess the joint probability for each and every possible configuration of the tag sequence and sum those probabilities together. Now, these two tasks are intractable to perform naively, but we know there is an algorithm called Viterbi and another one called forward that can address these two tasks in time O L, the sequence length, times t squared, t being the size of the tag set. So a rather efficient algorithm. And these two algorithms are in fact special case of something called the value recursion, which is what I'm going to teach you now. Okay, let me move this up here and highlight that the argmax problem in particular is equivalent to searching through the maximum in the joint distribution. And that's because the posterior can be re-expressed, as a conditional probability, which it is. And you can see that the denominator is fixed, is the marginal probability of our input. So whatever that number is, we might not know it at this point, but whatever that number is, it's fixed, it's constant, regardless of the choices we make for the variables C1 through CL. Which means we can discard it from the denominator and solve this perhaps simpler problem. All right? Okay, this is fixed. So let's talk about the value recursion, which will help us understand the Viterbi and the forward algorithm. And I'm going to talk about it by going through an example. And I'll start from the forward algorithm. Okay. So, we are in this example, the nice dog. We introduce our artificial symbols here. I'm going to shade with gray everything that we know, everything that we can count on having been observed. And see that I haven't written, but this is W1, this is W2, this is W3, and this is W4. And I'm going to circle in red what we don't know. So C1, C2, and C3. Okay, and for the sake of the example, I'm going to pretend that my tag set, C, calligraphic C, is A and B. See that in practice, you would have about a few tens of tags, and the EOS would be part of that tag set. The BOS would not, but the EOS would be. Otherwise, the algorithm can never stop. Now, the generative story can never stop. But if I had too many, I wouldn't be able to fit on my screen. So I have two tags A and B, two generic tags in there, A and B. Okay, and I'm gonna introduce a quantity that is gonna be called alpha ij, and that quantity is gonna be a marginal probability. Marginal probability of what? Imagine you have the sequence C1 through Ci, which are the tags for the sequence W1 through Wi, where W1 is the and Wi is whatever the ith word is. And this quantity alpha ij is going to be the marginal probability of all sequences that end with the assignment Ci equals j. That is setting the ith tag to making a choice for the ith position, and that choice being the jth tag in the tag set. So I'll give you an example. Let's say that we're talking about alpha 3b. So then we're talking about C1, C2, C3, C3 being set to B, C1 having generated the, C2 having generated nice, C3 having generated dog, and we marginalized out C1 and C2. What does that mean? It means we tried A, B, we tried A, B, B, we tried B, A, B, and we tried B, B, B. So we tried all these possibilities. We assessed their joint probabilities. And so on. And we added them up. That quantity, the marginal probability, is what we're going to store in this function, in this symbol, alpha ij. Now the interesting thing is that then we're going to be able to express something like alpha 3b using a function of alpha 2a and alpha 2b. By combining these numbers plus a few other things, we're going to be able to express alpha 3b. Similarly, by using alpha 1a and alpha 1b, we're going to be able to express alpha 2a and alpha 2b. So this will lead to a recursive algorithm or iterative algorithm, depending on how you implement it, which is a dynamic program that solves the marginal computation efficiently. So I'm not going to prove these results to you. I'm just going to state it, and it's here on the bottom left. I'll move it here more central. The forward recursion boils down to this. Alpha ij, which, like I said, is the marginal probability of the assignment where we've generated the words all the way up until the ith, including it. The ith word is being tagged with the jth tag in the tag set, and the sequence up until that variable has been marginalized out. So alpha ij when I is 1 evaluates to exactly this. It's a transition from the beginning of sequence tag symbol to the jth tag, and the jth tag then generating the first position. So it's always going to be this. When I is more than 1, then what we have is a recursive call to alpha again, but evaluated in the previous position. So essentially, to evaluate alpha ij, we check for all candidate tags that could sit in the previous position, and we assess alpha as if that tag was indeed the tag assigned to the previous position. And then we transition to the jth tag, and we emit the ith word. I'm going to show you this in a drawing, and it's going to make a lot of sense. So let's go have a look. Okay, so what do I have here? I have our example again right? So C1 generates the, C2 generates nice, C3 generates dog, C4 generates the end of sequence symbol. I introduce my artificial tokens here, and I show you the transition and emission probabilities. Take a moment to read them. Of course, I don't actually know C1, C2, and C3, and I'm interested in actually marginalizing them out, not in finding a specific assignment, for example, the most probable, but instead marginalizing them out, pretending these variables were assigned each and every possibility, assessing the joint probability of the results, and adding them up. Now, like I said, I will pretend my tag set has two tags, A and B. In reality, it would certainly be bigger. In reality, it would also include the EOS, but it would make my slide way too big. So just pretend I have two tags. So here are the possibilities for the first tag, A or B. Here are the possibilities for the second tag, A or B, for the second position. And here are the possibilities for the third position, A or B. So I'm interested in computing alpha 1A, which is marginalizing sequences that end in C1 being assigned A and then generating the. Alpha 1B, marginalizing all sequences that end in C1 being assigned a B and then generating the. And every other cell in this grid. For example, alpha 2B marginalizes all possible assignments of the preceding variables and assumes that C2 is assigned a B, and then we generate nice. Alpha 3A instead marginalizes all possible sequences up until C3 and assumes C3 is assigned an A, and then generates dog. And there is a special cell, alpha 4 EOS, which essentially marginalizes all possible sequences that end with C4 equals EOS and then generating the end of sequence symbol. That would be precisely the marginal probability we are interested in. This is the marginal probability. Right? Because it evaluates the joint probabilities of all sequences and adds them together. So this is the cell we are interested in. I'm going to start from the left though and work my way towards the right. It kind of gives you a good idea of how to implement this in an iterative fashion. Let's start. At the very beginning, I know that there is no sequence to be marginalized out prior to C1. So I know that to get to this cell, I had to do a transition from BOS to A, and then emit from A the. To end up in this other cell, I had to do a transition from BOS to B, and then emit from B at the. Things begin to get more interesting. Well, therefore, this is precisely what alpha, this quantity is precisely what alpha 1A should evaluate to. And this is precisely what the quantity alpha 1B should evaluate to. Things start to get more interesting as you progress. To get to this cell, to this quantity, we would have to know we would have to consider the possibility that we are transitioning from an A to another A and then emitting from this new A the word nice, or we would be transitioning from B to this A and then emitting from this A the word nice. Hence, this cell, alpha 2A, would evaluate to alpha 1A times this transition emission pair plus alpha 1B times this emission transition pair. This marginalizes the assignments to C1 and generates the last pair. All right, let's continue. Let's continue now from, well, let's try to evaluate this cell. So the marginal of all sequences that end with the pair C2 equals B, W2 equals nice. So we might have this pair by extending a sequence that ended in C1A, in which case we need to transition from A to a B, and then emit from B the word nice. Or, this is times, we continue from C1B with a transition from B to another B, and then an emission from B to nice. So we would go this way, or that way. We would combine alpha 1A times this transition emission pair plus alpha 1B times this transition emission pair. And this is precisely the value of alpha 2B. And we go on precisely like this. So let's think about alpha 3A. So this is the marginal probability of all sequences that end with C3A W3 dog. So let's see what we get. We get either we continue from a sequence that ended in C2A, and then we introduce a transition from A to another A, and then emission from A to dog, or we continue from a sequence that ended in C2B, and then we transition from B to an A, and then we emit dog from A. And this is precisely the value of alpha 3A. And we can do the same for alpha 3B. These are the sequences that end in C3 equals B, W3 equals dog. And we might have extended a sequence that ended in C2A, in which case we have a transition from A to B and an emission from B to dog. Or we extended a sequence that ended in C2B, and then we have a transition from B to another B, and from this B we emit dog. And this is precisely the value of alpha 3B. Last but not least, in fact quite important, alpha for EOS is the marginal probability of all sequences that ended in EOS. And a sequence end of sentence token. And of course, if we marginalize all sequences that end here, we marginalize all possible tag sequences for the sentence the nice dog. And this is the marginal probability we're looking for. And we can get here by extending a sequence that ended in C3A, transitioning from A to EOS, and then emitting from EOS the end of sequence token. Or we extended a sequence that ended in C3B, and then we transition from B to EOS, and then we emit EOS. We emit end of sequence token from EOS. And this is the marginal probability we're looking for. And this is the forward algorithm. All right, so that was the forward algorithm. And now we are going to go back to this part and realize that with a couple of transformations, this becomes another algorithm. So now I want it to be no longer the marginal probability. I want alpha ij no longer to store the marginal probability, but instead to store let me change the color. This one. I want it to store the probability of the best sequence, tag sequence, ending in ci equals j, where wi equals whatever the ith word is. So the setting is still very similar, with the difference that now instead of marginalizing out the assignments, we are choosing an assignment that corresponds to the best possible assignment measured in probability mass, in amount of probability mass. To obtain that, again, I'm not going to prove the algorithm, I'm just going to state the result. We can use the Viterbi algorithm. Now, the Viterbi algorithm uses the exact same value recursion, well, something very similar, to the value recursion that you see here, with one tiny difference. Implementation-wise, it's so tiny. We are going to be maximizing our choices, over the exact same set. So what is it? So the probability of the sequence that ends in ci equals j and emits the ith word from the j tag is either the probability of this transition emission pair when I is exactly 1, or for I larger than 1, we have to go and try every possibility for the previous tag, for the previous position. It may have ended in any one of the tags that are possible in the tag set, and from that choice we proceed with a transition emission pair that is appropriate, meaning the one that uses the corresponding tag, and again that emits the correct word. Now, whereas before we summed the probabilities of all these alternatives, this time we're going to pick the one that is maximum, that has maximum probability. I'm going to show you again in this example. So let's start up here. So the probability of the best sequence that ends in C1A and then C1 generates D has this probability. Well, this is the probability, right? So transitioning from BOS to A and then having A generate Z. So for the first position, it's just like before, nothing changes. For the second option, for the same position, we have a different transition emission pair, transitioning from BOS to B and then emitting Z from B. Things get more interesting as we proceed. So let's try to derive this one. So I'm going to try to derive this one here, which is the best sequence that ends in C1, C2A, W2 nice. Right, so the best sequence that ends in this pair, gotta continue from the best sequence that ended in A, and then we need to incur a product by a transition and an emission probability, or it has to, oh, I didn't mean to delete, or we continued from the best sequence that ended in C1B. Well, this time, we only need to know which of these two options will lead to the best value. So we are maximizing our choice. Let's suppose, for the sake of the argument, that this choice here has the highest product. So let me actually decorate not the A, but the arrow. This arrow here has the highest contribution. So alpha 1A times lambda A2A theta A2 nice is the biggest of the two possibilities, the other being alpha 1b times lambda b to a, theta a to nice. If this is the maximum value, here we will store that value, so that's the value of alpha. And let me just keep a little tiny bit of information here, which is a back pointer. It tells me the choice that the edge that maximized is the edge that came from A. Now let's do this one, alpha 2b. So alpha 2b should be the probability of the best sequence that ends in C2b, W2 nice. So we've got to continue from the best sequence that ended in C1a, or we've got to continue from the best sequence that ended in C1b. We compute the contribution of each of the edges towards the maximum probability, and we maximize our choice. And this is what we store in alpha, the max of these two. Let's suppose at this time, this is the best value. So I'm going to keep here a little trace of information saying that, actually no, let me change, sorry. Let's say that again, this edge was the best one, well, the edge from A. So I'm going to leave a trace saying that I maximize my choice when I continue the sentence, like the tag sequence that ended in C1a. Let's try to solve these two. So by now, we are pretty comfortable with it. We know this is the probability of the best sequence that ends in C3a, W3 dog. And we've got two options. We can continue sequences that ended in C2, best sequences that ended in C2a, or best sequences that ended in C2b. Let's suppose that, so we compute their contributions. Alpha 2a times this emission transition pair, competing with alpha 2b times this emission transition pair, and we maximize our choice. Let's say that this time, this is the best choice. So this time, we extend the sequence that ended in C2b. Let's solve this one again. So here we are computing the probability of the best sequence that ends in C3b, W3 dog. And for that, we have two options: to continue from alpha 2a or to continue from a sequence that ended in 2b. The probability of this extension is alpha 2a times this transition emission pair. The probability of this other extension is alpha 2b times the probability of this transition emission pair. And again, we maximize our choice. Let's save that this time. We're better off perhaps from here. Let's pretend that numerically this is the edge that has the highest probability of the two. Let me clean up. So I'm going to leave a trace that I better come from a sequence that ended in C2b. Okay. Last but not least, we solve the probability value of the best sequence that ends in C4 EOS W4 end of sequence symbol. And if we have the guarantee that at this point we have the probability of the best sequence that ends with this pair, then we know we have tagged all of the relevant tokens. So again, to get here, we either extend a path that ended in C3a or a path that ended in C3b. If we did this, it's alpha 3a times the contribution of this transition emission pair. If we did this, it's alpha 3b times the contribution of this other transition emission pair. And once again, we maximize our choice and store the value in alpha for EOS. And perhaps this time, let's say that this time, this edge here at the top is the best one of the two, and I have a trace saying, well, to get here I better use the path that ended in C3A. So what do we get here? Well, this value is exactly the probability of the posterior mode, which is the sequence. Sorry, what I said is incorrect. It's the joint probability of the best tag sequence measured in probability. This is not the probability of the posterior mode, because to be a posterior, we have to normalize this by the marginal. And instead, this is a joint. So in here, we have the probability of assigning WI, of generating the sequence, the nice dog, and a specific tag sequence, which we can reconstruct here. So I'm going to show you, we can do a backward pass and obtain that sequence in reverse. So actually I'm going to do it a little cleaner. So let me clean up a little. We have here the probability alpha for EOS is the probability of generating the nice dog end of sequence, and generating a tag sequence. And now I'm going to construct it for you, and we construct it in reverse. At the end we have an EOS. To get there, we chose an A. So to get here, we chose an A before. To get here, we chose a B. To get here, we chose an A. And to get here, we chose a BOS. Well, we don't choose the BOS, it's just part of the output. So we're done actually. This is the best sequence. The numerical value of this joint probability is stored in the alpha. And to obtain the concrete sequence, you need to backtrack following these pointers, these traces that I left next to the alpha. So if you maintain two tables, implementation-wise, you maintain a table of alpha ij values, and you maintain a table of back pointers, as they are typically called, then you have everything you need to both compute the probability and actually output the best sequence to the user. So there you have it. This is the Viterbi algorithm. I have one more thing to say. Oftentimes, we want to perform these computations in a logarithmic scale, because logs conveniently turn products into sums, leading to more numerically stable computations. So that's all very good. We just need to make a few changes to the recursion. So I'll put it on the side, and I'll just make a table here for you. So let's call this, which is like this things. I'm going to use another notation for it. I'm going to say there is a function S that gives me a score to the transition emission pair. Let's say there is a function plus, which tells me how to add two things, and a function cross that tells me how to multiply two things. By generalizing these two operations, sum and product, I can rewrite this in the so-called value recursion. Okay. And here is the complete table for you. I'm going to delete this here. I'm going to squeeze the recursion here on the side. And the complete table is as follows. So if you're interested in forward probabilities, then this is the transition times the emission, where you use the numerical real valued product that you know. Here you would sum, so A plus B is literally a quantity plus another, as you do with real values, and here you would multiply as you do with real values. If you compute forward in log space, then this is the logarithm of the transition plus the logarithm of the emission. This becomes the logarithm of the exponential of A plus the exponential of B. In NumPy, for example, this is called log sum exp, and you don't need to do the logs and the exps yourselves, so you get a stable implementation of that. And this becomes the log of A plus the log of B, because logarithm turns products into sums. Maybe I can squeeze this and get also the Viterbi. So we can compute Viterbi with the exact same type of score. Summations, well, the generalization of a sum here is the max of A and B. So semantically, what we mean here is alternative, and semantically, what we mean here is to continue to concatenate decisions. So numerically, for probabilities, this is sum and product. For log probabilities, these two operations. And for maximization, for Viterbi, you get maximization whenever you're confronted with alternatives. And you get the standard product whenever you're confronted with concatenation. Concatenate this decision with the previous decision, or these two decisions. And finally, Viterbi in log space. Well, the scoring function is the same, right? So it's the transition and the logarithm of the transition plus the logarithm of the emission probabilities. Logarithms are monotone, so maximization is not affected by it, right? So whenever you're confronted with alternatives, you maximize the choice, and whenever you're confronted with, whenever you have to concatenate two decisions, you take. Oh, I apologize. There is an error here. This is A plus B. The score is already a logarithm. We don't take a log again. So whenever we're confronted with concatenation of two options, we add their log probabilities. And here in the Viterbi log case, we do the same. We add two log probabilities. This gives you 4 algorithms for the price of 1. Yeah, if you're curious about this notation and what is the formal tool behind this kind of generalization, you don't need it for this course, but if you're curious to know more about it, it has to do with semirings. For this course, all you really need is to be able to understand conceptually and implement the forward and the Viterbi algorithms, be it in probability space or in logarithm space. Alright, I hope this helps.